So today we're going to shift gears a bit from machine learning to start talking about probabilistic modeling. Before I start though, I think a couple quick announcements. The homework was released yesterday. It'll be due 2 weeks from Thursday, I think. So it's more than 2 weeks, but not 3 weeks because of break. So if you just look at weekdays, it's a little bit shorter than normal, but not too much shorter. So you can count weekends in there however you want. But it's due. And also I should add, there's only one programming assignment for this. So it's a bit longer than the ones last time, but it's just one instead of two as normal. But then it'll be due a week from tomorrow at midnight. Yeah. Sorry, 2 weeks from tomorrow. I meant. Sorry, 2 weeks from tomorrow. Yes. I apologize. It's not due during break. No. Yeah.
So like it was released yesterday, right?
Yeah. Yeah, so it's like 8 days instead of your 8 weekdays instead of your normal 10 weekdays. Yeah, so it's 2 days less, and there's one programming assignment instead of 2. That was a trade-off we sort of went with. It seems reasonable. If there's a huge revolt against it, I guess we can reevaluate, but I think it seems reasonable. I mean, whatever we do, it's just going to be less time for the future homeworks, or essentially more crunch with your project in the future homeworks then. So we tend to think it's better off if everyone has a little more time for the projects and isn't crunched at the end with the projects. So this seems to be making the most sense. As I said, it is a bit shorter than the other one, so it seems to be a reasonable kind of middle ground. Okay, so let's talk about. And I guess the midterm should be graded and handed back relatively soon. We're aiming for tonight, but I'm not quite sure we'll make that. So by the end of the week, though, we'll have the midterm grades back. Yeah.
Will it be handed back in class?
I think we can hand it back in class, yes. So that will be, well, we can't now until after break, obviously. But the TAs will have it, so they'll email you your grades, and then you can go pick it up if you want to from them directly. If you want more than that. They're not going to scan it or anything like that. That would just take a little bit more time to scan everyone's. So you can pick it up from them if you're curious, or you can just find out your grade and then get it back in the next class. Okay, so let's get into probabilistic modeling. So, quick outline. I'm not sure I'm going to get through all of this today. It's actually quite a few slides, but I'm also going to go quite fast because the first material is mainly just review, or it should be review. If you have not seen this before, this will be pretty intense for a first time seeing probability, but that was one of the requirements we mentioned at the beginning of the class. So hopefully the whole first bit on background and common distributions is just review. And then we'll talk for a little bit about 2 topics that we'll focus on today, which is maximum likelihood estimation. This is actually a very common technique both in statistics and in machine learning. It kind of actually forms the basis for a lot of machine learning and how we come up with things like loss functions in machine learning. And then we'll start talking about probabilistic graphical models, though we'll talk about them not just in the sense of what you may have normally seen in an AI class, which is usually things like Bayesian networks, but we'll actually talk about them a bit more broadly in the context of generative models. Though really those two are actually quite similar, so we'll discuss what that actually means. We'll really use those 2 things interchangeably in this course. This is, as I said, the first of 3 lectures on probability. So next class after break, we'll talk about inference, and then we'll talk a little bit more about inference and Bayesian modeling. So I think actually the topics weren't quite aligned with how I ended up structuring it. So I've revised the topics on the course webpage too, and we'll sort of follow this overall plan. Okay, so let's jump into probability and AI. I mean, just as a quick background. So the basic idea here is that the world is probabilistic, at least at any sort of level that we are ever going to observe it at. And so that sort of stands to reason that our reasoning about it should also be probabilistic. And this actually, I mean, this seems obvious in hindsight maybe, or it seems just so apparent these days that everyone does this, but really this was a pretty major shift in the course of AI. So a lot of AI in the early 70s and beforehand, really, maybe even mid 70s or so, really focused on and then maybe even into the 80s now that I think about it, really focused on kind of a more logical description of the world. So there were predicates about facts about the world that were manipulated with logical rules, and this kind of was how we represented knowledge in the context of AI. And that really shifted a lot during the 90s. So in the 90s, there was this big shift to think about AI much more as a probabilistic field, and sort of think about our knowledge in terms of making probabilistic statements instead of just purely logical true or false statements. And as I said, this is sort of almost kind of second nature now. Every field of AI has really been permeated by probability. But at the time, it was very much kind of a revolution. This was not how people thought about knowledge, about facts of the world. People thought about them in terms of logical rules. And this has been a really important shift in kind of the focus of AI, really starting probably in the 80s. And now even areas which don't seem like they're probabilistic inherently, things like machine learning maybe is, but deep learning, neural networks, right, maybe wouldn't be seen as being probabilistic, but there really are probabilistic versions or interpretations or inroads in virtually all areas of AI these days. And so I'm going to give two quick examples. They're just sort of small examples, but then they also highlight sort of different aspects of what probabilistic modeling can do beyond just counts and stuff like this, and beyond machine learning too. Though we'll talk today about how machine learning ties in with probability as well. I guess it also depends on how broadly you define machine learning, because this could be considered machine. They could both be considered machine learning too, but the names sometimes are hard to hard to quite box in. So one of the examples, and we'll actually think about this a little bit later as well, is a technique called topic modeling. And so this really actually became sort of by this name, at least, and sort of as a field in machine learning and AI, really kind of evolved really pretty recently over the last decade or so. And one of the more common techniques in topic modeling is something called latent Dirichlet allocation, or LDA. And this is a technique that basically lets the algorithm read documents. So in this case, the algorithm read a bunch of articles from the Science magazine, 17,000 articles, and it determines kind of in an unsupervised fashion, that is with no explicit sort of anyone telling it what the things are about. It comes up with groupings of different topics for the articles, as well as sort of the key words that are in the different topics. So in this case, this is a figure from one of the original LDA papers. Sorry, this is a review on the LDA paper. This is not the original one. that's far after. And I guess the original one goes back, I think, 2003. So it goes back further than a decade, I guess this has been going on for. But in this case, they read 17,000 science articles, and sort of all on its own, but based kind of on sort of the co-occurrence of words and things like this, it was able to kind of split out different topics that the articles in Science cover. So if you look at some of those keywords, the first column here all has to do with things in genetics. So the title genetics was not given by the algorithm. That was just labeled after the fact by a human. But the algorithm kind of discovered all these topics kind of or all these words rather in the first column seem to relate to kind of a coherent, consistent topic in the documents. So they co-occur more often together, and they don't occur so often with other words. Is essentially the high-level idea. Though of course the details are more involved than that. And there's other categories like disease, evolution, or computers. These are sort of high-level topics that occur in science, but which are defined or really sort of generated through certain words that sort of link to that topic. This is actually a really common thing when you have a large, given especially just how much unlabeled free text there is these days on the internet. There's sort of a big desire to try to categorize things and understand the meaning of things without having to have a human label each one. And so methods like topic analysis and topic modeling are very common here. Yeah. So no. So the topic names are given after the fact. It comes up with the groupings of words, but these words all relate to a common topic by the model's sort of definition, which we will actually talk about later, and if not today, then the next lecture. The groupings of words themselves are what the algorithm produces, and then it's sort of very apparent to a human that what's really happening here is that they are grouping together similar words on a topic like genetics.
specified, or it comes up with that as well?
There are both types of models. You can have ones where there is a fixed number of them, and you can have them where they can sort of do however many you want. In traditional LDA, you specify the number of topics, but there's variations that actually say they're what are called non-parametric models, where there can be as many as you want. All right, so one more example, which I think is also a very cool example about sort of discovery of some sort of truth in the real world, comes from computational biology. And in this example, the goal is to figure out how the presence or absence of proteins in a cell can affect the presence or absence of other proteins. And so this is a topic that's widely studied in computational biology, or in biology as a whole. And it typically is a pretty time-consuming process to do things like this, right? Because you have to, essentially, every time you want to know there's an interaction, you set up an experiment to say, okay, I'm going to add this protein and then remove it and see what happens to these other proteins, see how that affects it. And it requires a lot of lab work, a lot of people sort of at desks with pipettes putting a bunch of things together. But with the advent of sort of more data-intensive processes, so I don't pretend to know the details here, but there are these I'm actually blanking on the word right now, but there are these things essentially give lots of different sequences and sort of different data points for lots of different presence and absence of genes in a cell, of proteins in a cell. And you can look at kind of, instead of sort of doing each experiment individually, you can look at just kind of the existence or absence of proteins on a very, very large number of data points and try to infer the causality or the co-occurrence from that. And so this is actually an example of a case where they looked at some of these I just don't have the thing here, what it's called, because I'm blanking on the name. But again, if anyone knows comp biology or comp bio stuff, you can certainly correct me here. But they basically take a bunch of experiments where they have sort of the presence or absence of these proteins, and they inferred this causal network that essentially tries to say, does the presence or absence of one protein cause or at least correlate with the presence or absence of another? And what they found was they actually can do this from a purely data-driven way, and they get most of the interactions that people kind of knew about already, but in a much less human-intensive process. So if we want to start sort of mapping a huge number of protein interactions and sort of figure out what's important in the makeup of a cell, then it's very useful to be able to do these sort of data-driven and automatic inference techniques that work in this matter. Now, of course, these things have to be probabilistic because it's not as if these are binary relationships. These are all kind of probabilities in terms of will the proteins co-occur or not, how will they affect one another. They're all about sort of seeing law of large numbers and seeing, doing a lot of experiments here. So these things really have to work probabilistically. But with those two quick examples in mind, and we'll cover both of those a little bit more later on, especially the topic modeling one. But I want to now sort of just go back to the beginning here and just give a very quick rapid-fire introduction to probability, at least as we're going to consider it in this class. Mainly to establish notation, because one thing I find about probability is that one of the hardest things for people is just understanding what certain terms mean when you write them down. So I'll try to codify that at least, but I'm going to go through this very fast. So if any of this seems confusing, I'd really recommend you kind of review the notes afterwards, the slides afterwards. All right, so let's start off. We are going to be, I should add, we are going to be informal here about probability. We're not going to go to a measure theoretic definition or talk about filtrations or anything like that. We're going to talk about at a very sort of informal level what these things are, but we're going to go there, through that very quickly and kind of use and then move on to what we can do with probabilities. Okay, so the starting point here is going to be random variables. So a random variable, again, very informally, is a variable whose value is not initially known. It's going to take on some value, but we don't know what it actually is. And these variables take on different values with certain probabilities. Again, that's a somewhat circular definition there, I know, but that's hopefully everyone understands what I mean by that. Where the probabilities essentially are a value assigned to each value that the random variable can take on, and these numbers have to sum to 1. So if you have a variable like weather, like what is the weather today, and that variable could take on the values, the discrete values in this case, sunny, rainy, cloudy, or snowy, the probability would essentially assign a number between 0 and 1 to each outcome. And those numbers have to sum to 1. And each of these corresponds to the chance that that weather variable will in fact be sunny, or which in this case is 0.3, or rainy 0.2, etc. Okay, hopefully this is not new to anyone here, or this is going to be a tough set of lectures. Okay, so one of the biggest things I actually find about probability is that one of the things that's hardest for people is understanding what symbols mean when I write something like p of x. Right, so I'm going to try to be, for the most part, consistent here, and I'm going to importantly do two things. So when I write p of big X, I'm going to use xi's to refer to random variables here. So xi will refer to a random variable, not an element within that random variable. So importantly, xi is itself a random variable. So we're going to talk about sort of combinations of lots of these things. Then p of big xi is going to refer to the set, really, or really function of all probabilities. So this number here, this notation here really refers to a function that can map any value that xi takes on to its corresponding probability. So p of big X means kind of the set of all probabilities. So it's called a fact, or more generally, it'll be what we call a factor. But this is, when you see this, think of a set of numbers that assign a probability to each value this could take on. Right? That is in contrast to this, p of xi equals little xi, which is going to be the probability that this random variable takes on this value, or abbreviated just p of xi, little xi. That is a number. Okay, so this is a number. This is the actual the value of that probability. Right? Now, oftentimes, people will not distinguish here between these two. And this causes a lot of confusion, actually, when you read papers on probability, because you don't quite know what they mean when they write this. Is this a random variable, or is this a value? I don't quite know. I'll try to be consistent, but the reality is you will see inconsistencies here, and so you have to kind of get used to them, too, when you read probabilistic. At least in AI, when you read these things, people are very imprecise here. The reality is most of the manipulations you do follow the same, whether you're applying it to values or to the random variables themselves. These actually mean the same thing. And so people are a little bit loose with notation. But just know that this is a fact of life. Right? People that are in this field know this, right? So importantly, this set of all probabilities, basically a function mapping values of the random variable to the probability. This one, just a number. We don't just write, I mean, ideally you would just write p as the function, right? But that doesn't really make sense because that doesn't indicate which random variable we're talking about. So this one's the actual function in some sense. Okay, so a few examples here. So say we have two random variables, x1 and x2. x1 takes on the values 1, 2, 3. x2 takes on the values 1 and 2. In this case, p of x1 comma x2, both big x1 and big x2, refer to what we call a joint distribution. That's, again, because they're big variables here, this is the set of all possible assignments to those two variables and then the corresponding probability. Right? And that's called a joint distribution. Conversely, p of little x1, little x2 is a number. It's just the probability that x1 equals little x1 and x2 equals little x2. And you can mix and match these things. So something like p of big x1, little x2 is the value, the probability values for each value that x1 can take on given that fixed value of x2. Okay, so x2 here is a fixed number, and this essentially corresponds to the function that maps all possible values of x1 to a corresponding number. Now, importantly, this here is not a probability actually, right? Because it's not a probability over x1 because its values don't sum to 1. They sum to something else that corresponds to the probability that this really they sum to p of x2. That's what they actually sum to. But these things, that when we write them, also when we write things like conditional probabilities, they don't actually sum to 1. So it's important not to think of them, everything we write in this way is a probability, in the strict sense of being a probability. And that's why we use the term, the word factor to describe these things. So these are all factors. This is a factor. This one here is a factor. This is a factor. As we'll see in a second, the probability of x1 given x2 is a factor. And so we're going to use that term generally to speak of things like probabilities that just don't need to sum to 1. Any questions so far? All right, so the last kind of rule we have is that when we talk about applying operations to probabilities, what we're really meaning, if we have two factors, say p is a factor over x1, I shouldn't say p because they're all p. We have one factor over x1 and x2. I have another factor over x2 and x3. Again, these are big. One of the other problems is that big x's look the same as little x's when I write them on the board. So unfortunately, depending on how my handwriting is going, it might be confusing. But hopefully they're all, I mean, they're all there that I'm writing down. So hopefully there's isn't any ambiguity. If you want to know whether I'm writing a big one or a little one, just raise your hand and I will clarify. But these are two factors. In other words, they are both functions that map from possible assignments to these things to some real number. We'll think typically about positive factors. We won't think about factors that have negative values. So even if they don't sum to 1, they're still all positive. And we can do things like apply operations to these things. And what that means is this is a factor over these three variables, right? x1, x2, and x3. And I'm going to have some operation here. And what that operation means is the result of this operation is a new factor, a new, in this case, probability, but depending on how you do it, if it's a probability or not. Depending on what operation it is, it could be a probability or not. But what that means is the result of this thing is a new factor over all the union of all the input variables here. So this is now going to be a factor over x1, x2, and x3, where that factor is just equal to, for each setting, is equal just to the operation applied to the individual numbers themselves. The factor is over the union. The factor is over the union of the variables. It is the number of elements in the factor will be the Cartesian product of those two. Yeah. So this is a new factor over the variables x1, x2, x3, and each corresponding value just takes on the value of little x1, little x2, operation little x2, little x3. So this is important when I write things like probability of x1 times the probability of x2. Even if there's no, these are each factors over this variable and over this variable. So if there's say binary variables, this would have two numbers. The probability is equal to 1 and equal to 2. You don't need all those to store those because one's just the negative, the one minus the other one. But this is essentially a factor that has two entries. This has two entries, and so this multiplication would be a factor over both these two variables that has 4 entries. Right? So that's sort of the basis, and actually, if you just get used to that, then a lot of this is much simpler. So a lot of this can be actually not that complicated. And all the rules I'm going to write afterwards, which you've seen, will actually be sort of using this kind of math implicitly, but we don't write that. We don't bother with sort of writing, define this as this for all of them. It's just sort of assumed you know. And by the way, this is sort of why people are a little bit cavalier, right? Because this thing kind of means the same as this, right? This is just, this thing applied to each possible setting of those variables, and so people kind of get a little bit loose with this and don't really distinguish between the variables themselves and the values they take on sometimes. Because all the rules we'll see actually kind of apply the same way to if you use an individual variable or the factors themselves. Yeah? So
if I'm thinking of like one of these variables like x1 as a function from some domain to R or something.
Yep.
And is all this, are you just saying that most of the operations we care about are calculated point-wise?
I think so. Again, it isn't that x1 is the function, because really it's p of x1 that's the function. But yeah, essentially, exactly. Every operation you care about is pointwise. But pointwise is sort of weird because you have the Cartesian products too, right? So you know, I don't know if I'd call this pointwise necessarily, because it's an operation over, you know, this is one factor and then this is another factor, and their product is a bigger factor. So I wouldn't call it quite pointwise, but yes, it basically means that you can just break them down into their individual assignments, apply the operation there, or, you know, of each variable, apply the operation there, and that gives you the actual values. All right, so once we have that, now sort of basic probability is actually just a few set of rules, and you can actually define the sort of a few basic rules of probability that from which all these other things flow. Sort of some of the basic axioms. I'm not going to do it that way. I'm just going to give the rules that people actually sort of use in practice. But of course, these things can all be kind of defined a lot, much more formally than what I'm doing here. So the first thing that you may sort of that we're going to the first thing we're going to talk about, and a very common thing that you will see, is something called conditional probability. So conditional probability is written P of x1 given x2. That bar there is pronounced P of x1 given x2. And this is just equal, by definition, to the probability, the joint probability of x1 and x2 divided by the probability of x2. Again, where those operations are applied element-wise. So, you know, for each assignment of x1 and x2, to compute P of x1 given x2, you would plug in the corresponding values there, and that would give you a probability. Now again, P of x1 given x2, with the big variables, is a factor over x1 and x2. It's not a probability over those two because it doesn't sum to 1 if you consider all the factors. But it is a conditional probability of x1 given the value of x2. And kind of importantly, I would say this can be written both ways. You can write it as P of x1 given x2 equals the joint probability divided by probability x2, but it's just as common to see it written as the joint probability P of x1 given x and x2 equals P of x1 given x2 times P of x2. Hopefully I pronounced that all correctly when I said that there. I'm trying to avoid writing too much down here because I do want to move on, but I'll try to write down the important things. And again, hopefully everyone has seen most of this before. And this actually leads to something called the chain rule. So basically what you can do is you can apply this thing iteratively. And what you'll see is that if you have a set of a lot of variables, probably of x1 through xn, this is equal to the product of the conditional probability of xi given all the variables that occur before it, kind of in order. And so that's a general rule. This is not an assumption. We're making no assumptions about independence here. This is just called the chain rule, and you can apply it to transform any joint probability into a product of conditional probabilities. The next thing we'll talk about is marginalization. So this is given two random variables, x1 and x2. To get the probability of x1, you can sum out over all the values of x2. Right? And you could write that sum either in terms of the joint probability distribution or in terms of the conditional distribution, which you know are the same thing. Just one is just applying the definition of conditional probability. Right? So this is the simple case at the top. And then, of course, we can also do this over many variables. So you can take the probability of x1 to xi in some set is equal to the sum over all remaining variables, xi plus 1 to xn. You sum over all their values, and that gives you the remaining probability. Again, hopefully this is review to most people here. And then for this to be a distribution, the case that we need is that if we marginalize over all the variables, so we basically sum over all possible values of them, we get the number 1. I should have had some quizzes on sort of what the size. I omitted the quizzes on the size of these things and like what they are, but that actually would have been a good one to include. So next time. Well, not next class, but next time we teach this class is what I mean. All right. So now there's these sort of the famous Bayes rule, which you probably have heard about, but which also hopefully you've seen questions like this before. So Bayes rule is just an application of really the definition of conditional probability, and then sometimes also followed by the definition of marginalization. The idea here is if I want to express, I have two variables, x1 and x2. I want to express, let me just make sure I'm in the right order here, x1 given x2. I could write this as just by the definition here, x1 and x2, given x p of x2. And I can now expand this one the other way. So write it, of course, this is just doesn't matter what order you do these things. So you can write this one as probability of x2 given x1, probability of x1, over probability of x2. But in fact, I'm going to take the next step there and just also write this in terms of the joint distribution where I then marginalize out x1. So this is then equal to the sum over all little x1 of the probability of x2 given little x1. I mean, I could write this like this, right? The probability of x2 and x1, but I'm going to write it, take one more step, and write it like this. Right? And that's how Bayes' rule is typically written. And so the nice thing about Bayes' rule is it gives us sort of again, just following trivially from the definition of probabilities here. But it gives us a way to sort of answer questions that have to do with probabilities when we only have one conditional probability and not the other one. So this is sort of one of the most common examples. You'll see which it's going to be a poll on Piazza right now. But part of the reason why this is so kind of famous, I guess, for a really simple rule that just follows from definitions is that it sometimes leads to results that seem unintuitive. So here's an example. And again, I presume, how many people have seen this example or something just like it before? Okay, okay, good. So just to make sure everyone remembers this, I want to know if I have some rare strain of the flu. This strain of the flu occurs only in 1 out of every 10,000 people. But fortunately, there's a pretty accurate or seemingly accurate test for this flu. In other words, if I have the flu, it'll tell me that I have it 99% of the time. And if I don't have the flu, it'll tell me I don't have it 99% of the time. So that seems like good odds, right? And so then I go to the doctor and I test positive for this strain of the flu. What's the probability that I actually do have the flu? And is it 99%, 10%, 1%, or 0.1%? All right, so the poll's now open. I wrote rate instead of rare there, but doesn't make much difference to the problem. All right, is everyone? No, not everyone's voted. The nice thing about this is you can just approximate it, so you can always just guess if you don't quite know. Some people voted really fast, incorrectly too. So maybe take the whole "don't get the poll" result correct, or don't not to take that into account a little too seriously. But it's still for the best. It can lead to a lot of stress in class if people are being tested every second. And also leads to much more needling on whether or not it was possible to know the right answer for certain questions. So I think it's fine to make them not required, or not count for anything. All right, I'm going to shut it down now. Anyone else still waiting? Okay, closing it. Okay, so again, fortunately, plurality of people got the right answer, but less than I would have hoped. But I mean, the numbers here are approximate. So if you guessed any of these three, you might just not quite have the chance to compute it. But if you guessed the first one, this is what, of course, most people answer, right? That seems like the obvious one, but that's exactly the incorrect answer. And the way to compute this is through Bayes' rule. So I guess I should probably go through it, given that I think it may not be obvious to everyone why this is the case. But let's think about how you arrive. But the right answer, by the way, is 1%, about 1%. But let's think about how we get there. So okay, so we want to know, so say that x1 is the fact that I have the flu. Take on value 0 or 1. If it's 1, I have the flu. If it's not, I don't. X2 is I test positive. Right? We know from the sort of word description there that the probability that I test positive, so x2 equals 1, given x1 equals 1, is 0.99. Right? We know that the probability I test negative, so x2 equals 0, given x1 equals 0, is also 0.99. And we know that the prior probability, the probability of just x1, probability I had the flu without any other knowledge, is 0.0001. So now it's just a matter of plugging this in. So I want to know the probability that I have the flu. So I want to know the probability of x1 equals 1, given x2 equals 1. Which is just equal to, well, it's just this thing exactly. I won't write it again. It's the probability that x2 equals 1 and given that x1 equals 1 times the probability that x1 equals 1. Maybe I'll write it anyway. It's the probability that x2 equals 1 given x1 equals 1 times the probability of x1 equaling 1 over this thing again. This thing repeated, plus the other flip side of the coin, the probability that x2 equals 1, given x1 equals 0, probability of x1 equals 0. Okay. And so I can just now, all these terms, this term here is just this term repeated again. All these terms I have from my little table there. And so this is just going to be equal to, well, this one is 0.99. This one is 0.0001. This one again over 0.99, 0.0001, plus this one, which is the opposite of this here, right? Because it's the probability that x2 equals 1, given x1 equals 0. So this is 0.01 times the probability this is equal to 0, which is 0.9999, and this whole thing is about 1%. Right? And so the intuition here is that even though the test is accurate, and that it's 99% accurate, because the actual flu is so rare that if you test positive, chances are you don't have the flu, and you were just one of those 1% that tested positive incorrectly. Those are the better odds. And so even though you test positive, you're actually only about 1% likely to have the flu. Which, by the way, is much higher than 1 out of 10,000, right? So you still definitely have higher probability than if you didn't test positive at all, but it's not high still. Okay, so hopefully that everyone, because everyone raised their hand when I asked about Bayes' rule. They've seen that, but then the results didn't quite back it up. So hopefully your memory was jogged, or you just didn't quite have the time to write down that math in the time of the poll. All right. Next topic, and I guess we are moving fast again. Next topic is independence. So we say that x1 and x2 are what is called marginally or just independent without any qualifications if their joint probability is equal to the product of their individual probabilities. Right? And another way of writing this, so that's just that p of x1, x2 equals the product of the marginal probabilities of x1 times the probability of x2. Another way of writing this, which you'll see sort of very frequently, is that they are independent if the probability of x1 given x2 is just equal to the probability of x1. And this actually follows just from that first definition. You write the conditional probability using the definition of conditional probability. If they're independent, that term above factors into the product, and you can cancel the x2s there, so it just equals x1. Similarly, the opposite goes as well, so the probability of x2 given x1 is just equal to x2. And this is sort of actually an intuitive way of thinking about it, because what it sort of says is that my probabilities that I have over x1, if I am told the value of x2, don't change effectively, right? So they basically don't actually change if I know x2, and that's a nice kind of intuitive definition of independence. There's one other type, though, which is conditional independence. And we say that x1 and x2 are conditionally independent given x3 if their conditional distributions factor like that. So in other words, if the probability of x1 and x2 given x3 is the product of these probabilities. And x3, p x2 given x3. Or equivalently, the probability of x1 given x2 and x3 is just equal to the probability of x1 given x3. I guess I wrote that backwards there with the x2s, but they're the same, of course. Yeah?
Just notationally, what's the order of operations for commas versus bars? So like p of x1 comma x2, is that probability of x1 comma x2 given x3, or the probability of x1 and x2 given x3?
I see. So p of x1 given x2 comma x3 means the probability of x1 given x2 and x3. It wouldn't really make sense to say what's the probability of x1 given x2 and x3. It doesn't really actually sort of compute as a probability. I mean, you could say something like the probability of x1 given x2 times the probability of x3, but no, it means so I guess the order of operations is first commas and then bars, if you want to put it that way. But I didn't usually think about it that way because the second one doesn't really make any sense sort of syntactically. But it's the probability of x1 given x2 and x3. So in other words, for each setting of x2 and x3, I essentially have a probability over all possible values of x1. Again, these are all factors, so I'm thinking about all of these as essentially functions that take assignments to the variables and output a real number. Now, very importantly, and this is actually a really common mistake people make, is that marginal independence does not imply conditional independence and vice versa. Right? So you can actually have x1 and x2 being marginally independent, but not conditionally independent given some other variable. And you can have, of course, them being conditionally independent given some other variable, but not marginally independent. That's actually, I think that's all I'm going to say for now, rather than try to go through the examples of when that happens and give cases of when that happens. But just be very conscious of that, because that's a very common mistake people say. It says, it's usually that they're marginally independent, and people assume they're conditionally independent based upon that, and that's not true. And you can't go either way. The two things are not. There's no equivalence there. All right, marching right through expectations. Expectation of a random variable is just equal to it's the sum of all the values the variable takes on times the probability it takes on that value. Now, importantly, these only make sense, expectations, when the values it takes on are some numeric quantity. So you cannot take the expected value of weather for being sunny, rainy, unless you assign some sort of some numbers to those, what those things mean. Expected values make sense for variables that take on numeric quantities. And when it does, this is the expectation. It's the sum of all values it can take on times the probability it takes on that value. So if a random variable can take on two values, 0 and 1, and you think of them as actual numbers, then actually the expectation of that random variable is just equal to, in fact, the probability it takes on the value 1, because it would just be equal to, expected value of some binary variable x would just be equal to the probability that x equals 0 times 0 plus probability that x equals 1 times 1. So in this case, it's very simple. It's just equal to the probability is equal to 1. But in general, that's the formula. You can also have conditional expectations. So the conditional expectation of x1 given x2 is equal to the sum of the values it takes on times the conditional probability. And usually these are specified in terms of fixed values for the n, because usually you think of expectations as being a number. Note that there's a little bit of a difference here in that I'm writing e of big X, but that is still a number. That is not a factor. E of big X is a number because I'm summing over all possible values X takes on. And you can write things like e of x1 given big X2, and then that's actually a factor over x2, but I'm going to try to avoid that. So the expectations are always going to be numbers here. A few rules of expectation. The sum of expectations is equal to the expectation of the sums. So expectation of the sums there is equal to this, or I should probably first the other ways. The expectation of x1 plus x2 is equal to the sum of expectations, and that actually does not even require independence of the variables. So they can be dependent. They can have a joint distribution that does not make them independent, but it still holds true. So that holds true for any set of random variables, or any two random variables. And if they are independent, the expectation of the product is also equal to the product of the expectations. That one, though, is not true if they're not independent. So again, hopefully review for everyone. I keep saying that, I know, but I want to keep driving it in. And I think one of the last things we'll talk about, well, not quite, but one of the last things we'll talk about kind of in the background is variance. The variance of a random variable is the expected value of the random variable minus its expectation squared. Which is also, it can be written a little bit more compactly sometimes as the expectation of the random variable squared minus the expectation. When I write that, it sounds the same each way, unfortunately. But the expected value of x2 squared, or the expected value of x2 all squared, minus that thing, rather. Both are forms that you will see for the variance, and it's trivial to show that they are equivalent. And so this gives some notion of sort of how dispersed the random variable is, right? Because if it always takes on the value of its expectation, that isn't very random. In fact, it's not a random variable at all. It's rather sort of a point mass on that one value. But if it takes on sort of a very wide spread of values around its expectation, that means it has higher variance. In other words, the expected value of how much it deviates from its expectation is bigger. And that's kind of where the notion of variance, or where the idea of variance comes from. And we can also generalize this, by the way, to covariance between two different random variables. So for two different random variables, x1 and x2, the covariance is equal to the expectation of the products minus the product of expectations. A non-class poll now, but for two random variables that are independent, what is their covariance? Who said that? 0. Does everyone understand? Oh, can you explain why it's 0?
Because the expectation of x1, x2 is just expectation of x1.
Yes, exactly. So from the previous slide, if they're independent, this thing is equal to the product of expectations. So if they're independent, their covariance is 0. All right, two last little words before we move on. Because we will, in this class, deal with not just discrete random variables, but also countably infinite and uncountably infinite random variables. So everything I've written so far actually works with the exact same notation if we allow the number of assignments to the variables to be infinite, as long as it's what's called countably infinite, for those that care about that. But if not, don't worry about that. The only difference is that obviously our functions, p of x, can't be written in terms of, explicitly what is the value of p of x for each input variable. It has to be a functional form, actually. So sometimes it's kind of a cleaner formulation because we know p of x actually has to be a function. But a common example is something like this. So the probability that x equals k, this is for k from 1 to with the domain of k equals 1 to infinity, is 1/2 to the k. So that sum, the infinite sum there equals 1. And it is, all the exact same rules from before apply. In this case, just all the sums you see are going to be infinite sums instead of finite sums. You might wonder how we can compute infinite sums, but we'll get to that, sort of how we compute these things later. Because actually what we're going to do for the most part is deal with continuous valued random variables. So in the continuous world, we do have to actually use different notation now. So a continuous random variable is described by what's called a density rather than a probability function, where you can think of them as being very similar, though. A probability density is just going to be a function from the domain of that random variable to positive real numbers. Where two things. First of all, if you integrate this over some range, and now I have to actually use little x here. If I integrate this over some range, this is equal to the probability that the random variable takes on values between that range. That means that if I integrate over the entire space, all of R, that has to equal 1. But after that, pretty much everything kind of holds. Here I should probably, yeah. The one other thing I'll add is that it often, so this is called the probability density function of this random variable. It's just like but the reality is that it obeys all these same rules here. So you can use marginalization, you can use independence, all these things just as easily with the density function as you do with the probability function. It's just these are now truly functions instead of sets or even functions over some countably infinite set. We can also specify them using what's called their cumulative distribution function. Importantly, which is called the CDF of the variable. The probability density function is called the PDF. Importantly, this D stands for different things there. So there's no such thing as a cumulative density function. It's a cumulative distribution function and a probability density function. But the cumulative distribution function is just equal to, which I'll call like big F of A, is just equal to the integral from negative infinity to A of of P of X, which of course is just equal to the probability that the value it takes on is less than A. Less than or equal to A, I guess, but because this, the probability of exactly equaling any number is 0 for any given number. Doesn't matter whether actually you use strict inequality there or not, but I'll use less than or equal to. Okay. Good? Took longer than I intended, about by 15 minutes or so, but hopefully it was a good review. Yeah?
The integral for the cumulative distribution function.
Oops, I should be negative infinite. Yes, thank you. That wouldn't make much sense otherwise. That would be a very small range and defined for very few A. PowerPoint takes a while to save. All right. Okay, so now let's walk very, very fast just through some common distributions. In fact, I'm only going to go through these. These are really just for reference here. You can look these up on Wikipedia, and they have more information than you could possibly want about the distributions. So just as a quick run through of the ones that we may see. So the first one that we may see, which we've already in fact seen, is called the Bernoulli distribution. That's just the distribution over 0, 1 random variables. It is parameterized by a parameter phi, which is just the probability that variable equals 1. So we will see this a lot. I'm going to start moving to this notation of p of x equal 1 and then semicolon, some other stuff. And that semicolon actually means it's parameterized by that. So the parameter of this distribution is, we only need 1. It's just the probability that equals 1. And then, of course, probability equals 0 is just 1 minus phi. The expectation, as we actually talked about already, is just equal to phi. The categorical distribution is sort of the next obvious generalization of this. This is just a distribution now over multiple discrete values. So it's distribution over taking on values 1 to k. And it's parameterized by phi 1 to phi k, where each of those are between 0 and 1, and each of those is the probability that it takes on that value. Now, importantly, the sum of the phis has to be equal to 1 here for this to be a distribution. So we actually could parameterize it in terms of just the first k minus 1 of these and make the last one just 1 minus the rest of them. But it's a little bit more common to actually have a phi for each given variable there. Now, importantly, unless the numbers here actually make sense as numbers. So so the weather was a categorical variable, right? Where I could just call sunny equal to 0 and rainy equal to 1. But unless they're actually numbers that they correspond to, it makes no sense to take expectations here. So as I said, expected value of weather, even if I call 0 equals sunny, doesn't make sense to call that 2.5 because that could mean half rainy and half cloudy, or half sunny and half snowy, or whatever. It doesn't make any sense to talk about that. Unless they actually do correspond to numbers, then it makes sense to talk about expectations. Probably by far the most common distribution you'll see in all of statistics is the Gaussian distribution, because it makes math really nice when you use it. And it's has this form here, which I'm sure everyone's seen before. It is a continuous distribution over the real value. At least in this case, it's just over the over real valued numbers, and it's parameterized by two things: a mean mu and a variance sigma squared. And importantly, it's mean, and it has this density function. So again, with a continuous random variable, you have to specify the actual probability density function in functional form, because we can't enumerate the density for all possible values of x. So this gives the density of x, the PDF of x, as a function of x, and as well as the parameters mu and sigma squared. Now, this is not obvious, by the way. This thing, if you integrate it over the real line, integrates to 1. Very non-obvious, by the way. I think some mathematicians said that this was, the mark of a true mathematician is that fact is obvious to you as obvious to anyone else's. And that's a silly statement because it's not an obvious fact. It's also not obvious that the expectation of that thing, well, the expectation actually makes some sense, because that one's it's just symmetric around the origin, so the expectation has to be 0. It's not at all obvious, again, that it's variance. In other words, the expectation of the value minus its mean 0 squared is equal to sigma squared. Again, not at all obvious, but it is the case that the mean of this distribution is always equal to mu, and the variance is always equal to sigma squared. In fact, this is why we write it this way. You can write it in other ways as well, but it's just sort of nice to think about these things in terms of their mean and variance. And so it's very common to write the density in terms of these two numbers here. One thing which we will touch on a little bit, because we see it we will see it later, is multivariate Gaussians. So a multivariate Gaussian is the multivariate generalization of that Gaussian distribution. So this is now a distribution over vectors in Rn. And the form of this is now actually going to be, or the density here is now actually parameterized by two things. A mean vector mu and a covariance matrix, which we'll call sigma. And so the mean here is a vector in Rn, and the covariance is a matrix, which is n by n. And as you may sort of imagine from the names of these things, the mean of the ith element there is equal to the ith element of the mean. So the expectation of xi in this random variable is equal to mu I. And the expectation of, or rather the covariance, I should write, of xi and xj is equal to the ij entry of sigma. And the density function is something that looks kind of a little bit nasty there. It's a quadratic function, an exponential quadratic function normalized by some term that involves the determinant of the covariance matrix sigma. So the actual form of that is not going to be that important for us, but we are going to deal somewhat with multivariate Gaussians, and so it's useful to know kind of what these things are and what the density is and how to manipulate them, though we'll talk about that more if and when we actually need to use it. Who here has seen multivariate Gaussians before? Okay, most, but not everyone. Okay. All right, then if we use them, when we use them, I'll mention a few more facts about this. Despite the ugliness of this density function, they actually obey a lot of really nice properties, multivariate Gaussians, that make them very easy to manipulate. They're by far the easiest distribution to actually, multivariate distribution to actually get a handle on. And so there's a lot of things that are very nice about it that make them easy. That's why people use them in practice, because they don't always fit your data, but they're often very nice at doing things and manipulating. Just so people know, there is a whole class of other continuous distributions that we may see here, like the gamma distribution or the exponential distribution. Exponential distribution has the following density, and it has mean 1 over, it's parameterized by some parameter lambda, and it has mean 1 over lambda and variance 1 over lambda squared. If we get to this again, I'll maybe remind people what this is. But the reality is all these things, again, you can look up on Wikipedia what their densities and distributions, cumulative distribution functions are. OK, so the thing I actually want to get, and I actually never intended to get to the last topic today, but I hope to get through some of this at least of maximum likelihood estimation, is going to be actually the main topic we focus on for the rest of today. And so the question now that sort of motivates this is we're moving now from probabilities to statistics. And what that actually means is that probability really is about sort of the mathematical forms of describing probabilities. What stats is about given some data, so now that I'm actually given some measurements, how do I model this data using probability? So if you talk about fitting into the data, that's statistics. If you ignore data entirely, that's probability. That's a very simplified interpretation there, of course, but that's kind of where you typically see the line drawn between those two things. So the fundamental question of statistics, I think, is the following. If I'm given some set of data points, x1 to xm, and then I'm actually not going to, they can be, they could be binary value, they could be real value, they could be vector value, they could be anything. I don't really care about that just yet. But I'm just given some set of numbers, x1 through xm. M indexes over the number of different examples we have, like it did in machine learning. The question is, how can I pick a probability distribution that models this data well, that seems to fit that data? Now, of course, if I allow myself to search over the entire class of all distributions, this is a very hard thing to answer. Probably impossible, in fact, because there's an infinite number of possible distributions, and without any assumption, of course, it's not a well-defined problem. So what's an easier problem, though still not that easy, is to say, OK, what if I only allow myself to consider distributions of a certain what's called parametric form? In other words, I think about distributions p over big X parameterized by theta for some fixed class of distributions. And I just want to ask myself now, what element in that class best fits or represents this data? So now it seems much easier, because now our question of finding a distribution has boiled down to just finding a theta, right? Finding some parameters that model that data well. So how do I find those parameters? Now, again, that may seem like an easier question, but actually even there are multiple answers. So I'm going to give one answer, but know that there are other ways of doing this as well. This is not the only way you can do it, even though it is a very nice way of doing it. And the answer that we're going to give, for the sake of this course, is maximum likelihood estimation. It's a very intuitive idea. In fact, you might kind of wonder after seeing it what else you could possibly do, but there are plenty of other things you can do, it turns out. So the idea of maximum likelihood estimation is the following. If I am given a bunch of data points, x1 to xm, and some distribution, p of x, parameterized by theta. This is a distribution, discrete or continuous or whatever. I'm going to pick that I know, and I assume also that these things are independent. So they're independent observations of samples from this distribution, a little bit more formally. Then the probability of all these things, because they're independent, that's equal to the sum of the product of the probabilities. So the probability of observing these things under this model is just the probability of each xi, product from I equals 1 to m, each xi parameterized by theta. Again, this is just a number because this is for each little xi that's actually a concrete observation you've seen. So this is the probability of observing all that data. So what I'm going to do is I'm going to pick the parameters that maximize the probability of observing that data. Right, so I'm just going to pick parameters. I'm going to pick theta by just maximizing over theta the probability here. And maximizing products is often not that nice to do. Products of functions of like convex functions aren't convex. So what we typically actually do is we actually maximize we take the log of this thing and we actually maximize over theta the sum from I equals 1 to m of the log probability of xi parameterized by theta. And in fact, this term is so common that this term here we often just abbreviate L of theta. This term is called the log likelihood of the data. Yeah?
Are the problems equivalent, or are they just similar that people use?
The maximizing the log,
Yeah.
they're equivalent because the log is a monotonic function. So the maximum of, I can always just take the log of if I maximize the log of some function, that's the same as maximizing that function. Yeah. Again, this may seem obvious, but there actually are other ways of doing this as well. But we won't worry about those other ways. Okay, so let's take a quick example, which is a Bernoulli random variable. So let's say I have a Bernoulli random variable. That's a variable that's a binary variable, binary valued random variable. And I want to know what its parameter phi is. Remember, phi is the parameter, it's the probability that equals 1. So I'm given a bunch of samples, and each sample, again, either 0 or 1. I want to know what's the best estimate I can have for that variable phi. Sorry, parameter phi. Well, again, it kind of seems obvious here, right? Like, you take the number of ones, you divide by the total number of data points, right? That's, of course, the best estimate of the probability. But how do we actually get there? How do we actually know that's the case? Because the reality is we could do other things too. For example, I could take the total number of ones, add 1 to it, and divide by the total number we have plus 2. That would be also actually a very reasonable thing to do. Maybe I'm sort of guarding against, overestimation or underestimation, because if I only observe one random variable, maybe I don't want to just, always estimate 1 or 0 for phi without any sort of, without any kind of hedging against that. And so maybe even if I have a lot of random variables, I want to, avoid the possibility that we either are estimating 0 or 1, so I want to do something like this. So this is actually very reasonable to do also, despite the fact that that one up there seems obvious. So where does that obvious one actually come from? In fact, in that case, it actually comes, a lot of estimators give that same answer, but I want to just show where it comes from in the maximum likelihood sense. So let's think about this problem in the setting of maximum likelihood estimation. So if I have a Bernoulli random variable, then the probability of any xi given phi, right? We can write this kind of in an interesting way to make our lives a little bit easier here, relatively easier. If x equals 1, this probability, if this xi equals 1, this probability is equal to phi. If this xi equals 0, this probability is equal to 1 minus phi. So I can write this as phi to the xi times 1 minus phi to the 1 minus xi. Right? I can sort of simplify it and write it down that way. That is going to be a probability that's valid for any assignment of this thing. Okay? So now let's write down our log likelihood function. I guess I said I'm running as minimization here, but I'm actually running it as maximization. If you want to minimize, you just minimize the negative thing. So I'm going to minimize or maximize now the log likelihood of my data, which is equivalent to saying I want to maximize over theta. I can say the theta here is just my parameters phi though, of the sum over all my data, I equals 1 to m, of the log probability of that thing. So I'm going to take the log of this. This is equal to xi times the log of phi plus 1 minus xi times the log of 1 minus phi. Okay, so that is my log likelihood. And so now, if I want to optimize that, this is actually one of the cases where I don't have to resort to gradient descent or anything. I can actually optimize this analytically very nicely. So this actually, I do that by just taking the derivative of this thing with respect to phi. All right, so I'm going to take the derivative with respect to phi. I'm writing big D's here because this is not a partial derivative. This is a full derivative. There's no other functions it depends on here. Sorry, no other variables it depends on. But this is just calculus now. So this is going to be equal the derivative of the log likelihood. I always write theta there, but here it's really phi. It's going to be equal to the sum from I equals 1 to m of this thing. This is going to be xi over phi plus 1 minus xi over 1 minus phi. It's going to be that thing. And I can move the sums inside here. So this is going to be equal to the sum over I equals 1 to m of xi over phi. And why did I say minus? Oh, this is a minus, sorry. I have a minus on phi there, so this is minus. Minus the sum from I equals 1 to m of 1 minus xi over 1 minus phi. Okay? And I'm going to set this equal to 0. That's how I remember to solve a problem, to find its optimum. I set the derivative equal to 0, at least as long as it's a convex function, and this function actually is convex. You can verify this function is a convex function in phi. So it will have a unique, actually, it's a concave function because we're maximizing. It's a concave function in phi. That means it will have a unique maximum that we can find by saying its gradient equal to 0. Okay, so let's finish this up. We're going to call this term here is just a number of positive examples. I'll call this A. This is the number of observed zeros. I'll call this B. And so we have the equation A over phi minus B over 1 minus phi. Phi equals 0. In other words, phi is just going to be equal to phi is going to be equal to A over A plus B. Or in other words, we have the amazing statement that phi is equal to the number of ones we've seen divided by the number of ones plus the number of zeros. In other words, it's just the thing that we guessed in the beginning. So a lot of work, but now maybe you know where that amazing insight of counting the number of ones and dividing by the total number actually comes from, at least in one estimation framework. So this is sort of where we get, and obviously for Bernoulli, you could probably argue that you didn't really need to do all this stuff, but this gives us a very general framework for sort of computing these things for any distribution. And so we can come up with much more complex distributions, which we'll see in a second, and we get similar estimates for them. I won't talk about this now because I want to jump to the next one for a second, but you can do the same thing for a Gaussian distribution. So if I write the likelihood of a Gaussian, and you might want to check this if you're not confident on this or if you don't believe me. You could write the density of a Gaussian. You can take the log of that and look at the log of likelihood as a function of the parameters mu and sigma squared is equal to this thing when I plug in my xi's that I've observed there. If you set those equal to 0, the derivative of those with respect to mu and sigma equal to 0, what you'll find is that our maximum likelihood estimate for mu is just equal to the average of the observed data points, and our maximum likelihood estimate of sigma is equal to the average of the data points, the sum of the data points minus their mean squared. So that these two estimates, which are sort of the natural things you would think to do to estimate the mean and the variance of a distribution, are in fact the maximum likelihood estimates for the Gaussian likelihood. This is actually probably worth doing if you haven't seen this before. It's worth going through that math and just making sure that you sort of understand what's happening there. The last thing I want to say today, though, is sort of talk about this in the context of machine learning. So when I talked about machine learning, I did something kind of strange in that I didn't actually talk about probability at all in machine learning, which is a little bit odd, but I think it's actually fine to think of it that way because really it's about optimizing loss functions. That's what machine learning really is about. But to a large extent, things like where we come up with those loss functions may seem kind of arbitrary, right? So I talked about logistic regression. I talked about this loss function here, and I sort of motivated it, and sort of this was kind of like a smooth version of the 0-1 loss. But that's not how they came up with it, right? That wasn't actually the way people came up with this particular functional form for logistic loss. And also, on your homework and in class, I mentioned this other thing called a multivariate logistic regression function, which is called softmax regression, sometimes also called cross-entropy loss. And I just wrote it like this. I said, this is the thing we optimize. And that might have seemed really strange. Like what is that, and why on earth do we optimize that? So I want to motivate these two things now in terms of maximum likelihood estimation. And so I'm going to go through that very briefly. I think I'll just make the first one probably. I might skip the second one. But let's think about where this comes up. And I'm going to do it in one way. There's actually several equivalent ways you can do this. But I'm going to just do it in one way, which is a little bit simplistic maybe, but we'll see how it works. And in the 5 minutes I have left, I think we have plenty of time. So our goal in logistic regression, remember, is to model some conditional distribution, P of y given x, where y is a binary random variable, but it takes on values +1 and -1, not 0 and 1. So y takes on values, or really little yi is going to be in -1 and +1. And x takes on some other values there, but we're not modeling the distribution of x, we're just modeling its distribution of y, so we don't really care what values x takes on. But we want this to be some function of like a linear combination of our features. We want it to be some function of x transpose, theta transpose x for some parameters theta. This was kind of our machine learning model. So one very common thing to do is to say that this probability, the probability of any given xi, given, or rather, probability that I should probably write it as the probability that y equals +1, given some specified values for x, and really I should write here parameterized by theta. This term is going to be a probability, and it has to be, so therefore it has to be positive. So, and we're going to take logs of it, we know, when we take the log likelihood. So a very common thing to do is to say this is going to be proportional to the exponential of theta transpose x. Because we know this thing is positive. We know that when we take logs, we get a nice linear term. So it's kind of nice to model it this way. And this is where I'm kind of being a little hand-wavy here, but this is, there's more formal motivations. Don't worry, that's not how the basis for all this math, but that's sufficient for our sake. So this is my probability here. And actually, I could do the same thing for the probability that y equals -1, but because they're, of course, just opposites of each other, I'm just going to, and this means proportional to, I'm just going to define the probability of y equals -1, given x and theta, parameters by theta, as just being proportional to some constant. So, so this, it'll just end up being the opposite of this thing. So given these two proportionalities there, I have to normalize them to actually get my probability. So this probability is actually equal to the exponential of this thing divided by this one plus that one. Right? So that's our distribution of y given that's our probability that y equals +1 given x and theta. And this, by the way, also simplifies just to 1 over 1 plus negative, 1 plus x of negative theta transpose x. It's a little more common to write it this way, but it's the same thing. You have to write one less x and one less theta transpose x. This function here, or rather this function, if I put an arbitrary value z in there, is called the logistic or sigmoid function. It looks like an S curve, It's a function that varies between -1 and +1, and it's symmetric. Well, not symmetric. It's sort of, what's the term for this? I forget what it is. It's not symmetric, but something around the origin. The origin as value is 0.5. It's odd. It's an odd function. No, because not odd, because that would be, it has to be shifted down. So it's 0, at 0 is 0.5. At negative infinity goes to, sorry, as x goes to negative infinity, it approaches 0. S goes to positive infinity, it approaches 1. And it's sort of symmetric, rotated around itself 180 degrees around the origin, and 0.5. Okay, so this actually is all I'll say because we're out of time here. But the big sort of actual statement here is that if we look at that model and think about maximum likelihood estimation, so if we want to pick the parameters that maximize over theta, the sum, given some observed data from I equals 1 to n, of log probability of yi given xi and theta. Well, that thing is just the log of this. So this term on top doesn't matter. It's log of 1, which is 0. So it's the log of this thing, which is just going to be equal, which is negative log of this. And so this is going to be equivalent to minimizing over theta the sum from I equals 1 to m of the log of 1 plus x negative theta transpose x times y, xi, yi, which is exactly was our logistic loss function. So this is sort of how we came up, in fact, with the notion of logistic loss, the notion of logistic regression. That really just is going to be fall out of this maximum likelihood estimation under this particular probabilistic model. All right. The same will happen for softmax regression, actually, which we may or may not go through next time. But essentially, a lot of the choice of loss function in machine learning is, in fact, based upon these probabilistic notions. OK, that's all I'll say for now. Next time, we'll talk about graphical models, and we'll kind of go into probabilities when there's a lot more than just one random variable.